Chapter 6 is more on the body plots, and it's another method to investigate the system stability by using frequency response. Actually, we already talked about system stability when we start with chapter 4 by using graph table, and we learn how to use graph table to study the stability of the system and identify the system stability based on the location of the poles. Is it on the left half plane or the right half plane? Okay. Then in chapter 5 we talk about the usage of root locus also to investigate the system stability and to identify system stability. So we said the root locus represent the movement of the pole for the closed loop transfer function by changing the value of the gain from the open loop situation where the gain is equal to 0 to the infinity. Okay, so I mean we learn how to identify if the system is stable or not, and how to know the border or the crossing point with the imaginary axis, which is a point of changing the system from the stability to the instability. In this chapter actually the focus will be on the same criteria or the same performance metric of the transfer of the control system transfer function, which is the stability. And we are going to use a different method in order to identify the system stability, which is the body plots. So the body plots in this chapter, actually this is the aim of the chapter and the expected outcome, and these are the main content of this chapter. So we have the sketching for for a body diagram. For a body diagram here, we are going to sketch a body diagram. After we sketch the diagram, we are going to identify the system stability based on the diagram itself. First, we want to highlight or to define the frequency response, and frequency response method actually was developed before the root locus method. It was developed in the early 1930s and before the developing of the root locus. And the technique here has some advantage in some situations. For example, if we want to model the transfer function by from a physical data, also when we want to design a compensator, or I mean like lead or lag compensator, in order to compensate the error in the control system. So in this case it's better to use the frequency response method. Also when finding the stability of nonlinear systems, in settling some issue related to the root locus sketching. Okay, so this is some of the advantage of frequency response method. In the frequency response method actually is more focusing on the usage of the sinusoidal function as the input to test the system response. So previously in chapter 4, when we talk about the steady state response, we highlight three type of function, which is step function, parabola function, and ramp function. And we say these functions are used in order to test the steady state response of the control system. In for the frequency response, actually the focus will be more on the sinusoidal input to the system. We apply a sinusoidal input, then we measure the response of the system or the output of the system. The focus in this case will be more on frequency. So when we talk about frequency, we are going to focus more on the value of j omega. We said we know that S actually the S or the operator here for the Laplace operator, or we use it to represent the values of the poles, the values of zero. We said it consists from two parts, which is sigma plus j omega. So in this chapter, actually, our focus will be more on the j omega value or the frequency value. Okay, so we are going to focus more on the imaginary part of the pole location, and also of the frequency of the input testing function to the system. So for the frequency response system is here, we can define it is a steady state response. It's the same like the one that we have in chapter 4. which is steady state response. We apply input and we measure the output, but here the input will be more on the, or the type of the input more on sinusoidal input signal. It's not parabola, it's not ramp function and so on. So the frequency response here can be computed from a single for a single frequency, or also for a range of frequencies. So we can consider only one frequency in order to find the frequency response, or also we can focus on a range of frequency. Also, the dynamic of the steady state output here of the system, or the output of the system. If I have a system here with the transfer function of Gs here, we apply some input like sinusoidal input to the system. The output of this system will have the same frequency of the input, function, but the value, it will have different magnitude and different phase also. Why different magnitude and different phase? Because it depends on the transfer function of the system. So the transfer function of the system, which comes from the component of the system, is it electrical component or electrical component, will affect the value of the output function here, or the sinusoidal function, in terms of magnitude and in terms of the phase shift, not in terms of the frequency. The frequency for the input is the same as the frequency of the output of our system. So this is example here. We have a block diagram for represent the transfer function of the system Gs here, or Ts, is it for open loop or for closed loop, which is consists from magnitude and angle. As we said, Gs can be represented by magnitude and angle, as we mentioned in chapter 4. We said when we talk about the Kgs HS as a magnitude and KGS HS as the angle, which should be like an odd multiple of 180. Okay, so this is referred to the component of the system itself, and it will be given. That means they will say that transfer function for the system is represented by this value, either in term of S, then it's just replace the value of S by value of omega, or the frequency. Then you have the input function here, and the input function is the sinusoidal function. The output function, you can see here, the frequency of both function will be the same, only we can see the shift in the phase. So for example, this is start from that point, and after the zero here, there is a phase shift here, will be different. So you can see here how is the, or the value, or the phase of the signal. Also the magnitude here we have the magnitude of the input, but the magnitude of output will be equal to the magnitude of the input times the magnitude of the transfer function itself. So the magnitude is change, the magnitude is equal to the multiplication of the input times the magnitude of the transfer function itself, and the phase shift also change. So these are the two main things that change during the frequency response. For that, since we have magnitude change and phase change, the body plot method will focus on two type of graph, which is one related to the magnitude, one related to the phase. So here, this is the output function, m out of omega, v out of omega. This is the output. This represents the input, the m from the input. This one represents the m from the this from an input signal. This is the m from the transfer function. This is the phi of the signal itself. I mean, of the system itself. This is the angle of the input transfer. So here we have magnitude response, and we have also phase response. The combination of the magnitude and phase frequency responses, the combination of both magnitude and phase responses, called frequency response. So magnitude, phase give you the frequency response. So when we talk about the frequency response, we focus on the magnitude of the response, and also the phase of the response. When we say the response, means output of our system. So there are two types of body plot here. So the two types of body plot, since we have two type of responses, one related to the magnitude, one related to the phase. So we have two type of body plot. One, or the body plot straight line approximate the log magnitude. For the magnitude, we use the log magnitude here. We do not use the direct magnitude of the function. We use the log magnitude of the function here. whatever is the function, we are going to find the log of this function. Then this is for the the y-axis. For the x-axis, we are going to use the frequencies. Okay, so this is the first body plot, which is represent the relation between the log magnitude lm, log magnitude, and the frequency, while the second body plot, which represent the relation between the phase, angle, and frequency. So this is represent the angle, and here also the frequency. So both body plot, which the real axis, or the horizontal axis or x-axis of both body plot is represent the frequency. Since we have the frequency, this frequency actually it has a wide range of values. So usually when we talk about frequency, we talk about kilohertz, megahertz, gigahertz, and so on. For that, we use the magnitude. Otherwise, we cannot represent the body plot in a normal representation, because the value here will be 1100, 100,000, 10 to the power of 6, 10 to the power of 9, and so on. So we had a wide range of values, so it's not easy to represent by the normal magnitude. For that, we select, or they select the representation of the log magnitude, so it can cover a wide range of values. So both graphs or both body plots are plots regard with respect to the frequency or omega value. The log scale here, or the selection, this is the justification why we need to use the log scale, is used for body plot because of the range of frequency. So the range of frequency, we said, start from tens of frequency until gigahertz values. So usually the body plot is drawing or plotted on a semi-log paper. This is one as a specific type of the paper, which is divided by using the log values, okay, for the x-axis, and also link it to the value of the y-axis. This is how the log or semi-log paper is looks like. So it's divided here by log values like 10, then 10 to the for example here for 10 to the power of 0, which is 1, then 10 to the power of 1, 10 to the power of 2, which is 100, 10 to the power of 3, which is 1000, 10 to the power of 4, which is 10,000, 10 to the power of 5, which is 100,000, and so on. So this is how the semi-log paper is looks like. And as we said, for our body plot or body diagram will be uh, consists from two parts, which is magnitude and phase. Okay, so the part of magnitude usually in dB or decibel here, because it's calculated by using log of V out, for example, V2 over V1, or I2 over I1, or P2 over V1. It depends on what is the value that we are going to measure. So this is what we mean by decibels here. Decibels actually usually relate between two quantities. It's not we cannot say decibel for voltage, but decibel should be for two voltage, like V2 over V1, I2 over I1, V2 over V1, and so on. So you should have two values, and then you measure one value with respect to another value. This can be measured in decibel or in dB. For that, this is the formula how to find the log magnitude of the voltage in dB. It will equal to 20 log to the base 10 V2 over V1, 20 log base 10 I2 over I1, 10 log base 10 V2 over V1. And we can see here for the voltage at current we use 20, and for the power we use only 10, because actually the power equal to V times I. And when we talk about the power, the power also can be represented by V square over R, or I square R. So in both cases, if we have the two here for square voltage or for the square of the current, the two will be multiplied by the value of 10. So it will give you the value of 20. When you convert from the voltage to the power, voltage, and when you calculate the power in terms of the voltage or in terms of the current only. So this is the formula actually that they use to calculate, but this only to show you how to calculate the value of decibels. In the next video, we are going to talk about the body plot and how we can draw the body plot actually. So we need to draw two values, which is the magnitude plot and also the phase plot. And as we see, this is the closed loop transfer function or system, which consists from the forward transfer function and the backward transfer function. And usually we said in the body plot, we are going to use j omega instead of s. So instead of saying j of s equal to blah 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 here, we are going to say just j of j omega, because our focus will be more on the frequency of the system rather than or of the function rather than the considering the s operator in general.